Hello and welcome to the webinar. My name is Josh McDaniel. I work with the Wildland Fire Lessons Learned Center, and I'll be introducing the presenters and moderating the webinar today. I want to point out that this is a webinar series sponsored by three organizations. There's the Joint Fire Science Program, the Wildland Fire Lessons Learned Center, and the International Association of Wildland Fire. Okay, so today's webinar is a third webinar in a series that we're putting on smoke science. For the next several months we'll be hosting webinars covering some of the recent research completed by projects funded by the Joint Fire Science Program Smoke Science Plan. As most of you in the audience are aware, I'm sure you'll know that smoke and smoke management will likely increase in priority in coming years due to a combination of air quality regulations, increasing urban interface, and potential climate change impacts. And so JFSP research is helping to address that issue by validating smoke models and projections, improving understanding of smoke emissions and dispersion dynamics and chemistry as well, improving understanding of the human health issues surrounding smoke, and also looking at climate change. So today, Marko, Princevac, and Christian Bartolome are going to be talking about some of their work on smoke, but we also have some other upcoming webinars in the same series. The next one is next week. Young Liu is going to be giving a presentation on evaluation and improvement of smoke plume models. On March 4th, Talat Admin is going to be doing a presentation on predicting smoke impacts with uncertain emissions and meteorology. And then in April, Warren Heilman will be presenting on predicting local smoke dispersion during low-intensity wildfires in forested environments. There are a few others that we're working on getting scheduled that might fill in between some of these dates, and so you can find out about the schedule and get the up-to-date schedule and registration links and that sort of thing at this website. It's Advances in Fire Practice. I guess there's not a URL on there. This is one of the Wildland Fire Lessons Learned Center's subsites. So if you go to the Wildland Fire Lessons Learned Center, you can find this under resources, and then right there you can see all the webinars with links to the registration. Or if you're on one of the email lists for the Lessons Learned Center, we also send out announcements, and I believe JFSP is sending out announcements as well. And IAWF is probably posting on FireNet, so there's lots of different places you can find out about it, but keep checking back, and we're updating the schedule constantly as we get the presenters lined up. Okay, so on to today's webinar. First, in terms of questions, you're welcome to ask questions at any time, and we encourage you to get it in early, but we're going to hold a Q&A session at the end of the presentation. But the farther up the queue your questions are, the better chance we have of getting to them. We try to get to them all, but sometimes there's too many. But you can find that in your questions box or questions tab and your control panel over to the right. You can type in a question, and then we will read through them, and the presenters will respond to them at the end. And also, we're recording the webinar, and so it's a video file that's produced, and then that file is posted on the Lessons Learned Center's YouTube channel. You can come to Advances in Fire Practice and find the link. I'll have it right up there in that same spot where all the webinars are listed, or you can navigate your way to the Lessons Learned Center's YouTube channel and find it that way. Okay, so with that, I'll go ahead and introduce the speakers. First off is Dr. Marko Princevac. He is Associate Professor of Mechanical Engineering at University of California, Riverside, and he's interested in fundamental and applied fluid mechanics research, in particular the application of fundamental turbulence concepts to studies in environmental flows and fire dynamics. Also presenting is Christian Bartolome, and Christian's a PhD student at the University of California, Riverside, and he's been working on Superfog for the past 4 years and is now moving into looking at fire spread and crown fires as well. Okay, and with that, I will hand it off to Marko and Christian, and they can take it from there.
Well, thank you, Josh. I'm Marko Princevac, and I want to thank you all for attending our webinar on Superfog. Well, we hope you will find it informative and useful. And the presentation will be given, as Josh said, by my graduate student, Christian Bartolome, who actually did all the experiments, analysis, and coding of the Superfog Analysis Model. Well, with that, Christian, please go ahead.
Thank you. Okay, so today I'll be showing you the new Superfog screening tool. We abbreviate as SAM. That stands for Superfog Analysis Model. And this is the list of all of our collaborators. And we'd also like to thank the Joint Fire Science Program for funding all of our research related to Superfog. So prescribed burns are an excellent tool for land management. And as Josh mentioned, there's a lot of concern for chemistry related to the smoke and the hazards that smoke present. In this presentation, we'll talk mostly about visibility. So what happens is after having a prescribed burn, in the evening hours, in rare occasions, the smoke from the smoldering combines with the ambient atmosphere and creates a really dense fog that's called superfog. So this is for any visibility impairing fog that will cause less than 3 meters or less than 10 feet. These images below are from Gainesville in 2014, where there was a superfog event from a wildfire. Now, this fire wasn't a prescribed burn, but it's also a concern for land managers, maybe police officers who are interested in protecting the public in case of wildfire. So how does superfog? So some superfog's major events in the past. In January 2008, on the I-4 freeway in Polk County, superfog caused a 70-car pileup with numerous fatalities and injuries. In 2011, wildfires caused low visibility events, and then they had to close numerous highways for the Dismal Swamp Fire. In 2011, there was also a superfog event on the I-10 in New Orleans that caused 2 deaths and 61 injuries. The most recent I've recorded is in 2012 in Gainesville, which I showed the photos for earlier, where 7 semi-trucks, 12 cars were involved in. There's 10 lives lost and 21 injured. So I'd just like to show just an example of what it's like to drive through fog. So this is a low visibility condition. There's visual cues like trees in the road to help you drive through. However, in a superfog condition where visibility is less than 10 meters, you don't have any visual cues like before, such as the road or the trees. Nothing is visible beyond the hood of your vehicle. So it's easy to see how we could have such a major accident from having superfog on highways. So how does superfog form? Superfog, as I mentioned, forms from the smoldering of a burn area, and the main production from the smoldering area is water vapor and particulates. Now, in the evening hours when it's cool, the water vapor will condense onto the particulates and form water droplets. And so now you have these water droplets present. Wavelengths of light are scattered. So there's an extinction coefficient associated with the fog, and extinction coefficient is directly related to the visibility. So this is our we model superfog from various perspectives and combine them. So our first simple model is combining cool ambient air with the warm smoke, like I mentioned before. And then this will either create fog or it'll create an extremely low visibility fog or superfog. And so we use conservation of water and conservation of energy. And these together become our thermodynamic model. The way we use this thermodynamic model is to solve for final temperatures, final liquid water content. That's how much water in liquid form is available to form these droplets. So here we have a photo of Gary Ackmeyer, and in 2008 he made many measurements of smoke temperatures and smoke humidities. And we take the data that he collected and feed it into our thermodynamic model. And after many cases, we found like the high-end amount of liquid water content we have available is 2 grams per kilogram. And so we have an idea of superfog visibility, 10 feet, and the liquid water content. These two are linked by the size distribution of the particles, NR. So these 3 equations become the foundation for our visibility part of our modeling. So after we do visibility modeling, we can produce graphs relating how these variables are associated to each other. But the main part is here for superfog specifically, where the visibility is 10 feet and liquid water content is 2 grams per kilogram. These tiny fog droplets need to be the diameter of 1 micrometer, or the concentration of 10 to the 5th per cubic centimeter. So with this information, we move to another type of modeling, the dispersion modeling. So how high will this superfog go, and how does it spread? So here the z-axis is height and x-axis is the downwind. In our model, we'll have temperature and velocity measurements. You can download online or from MM5 modeling. And then we can apply heat flux and vapor flux. These are contributions from the smoldering. And our model makes calculations for temperature and humidity throughout the grid. And this becomes the basis for our SAM model that I'll mention a little bit later in the talk. So after we had a strong foundation on theory, we moved to experiments. This is a schematic and photos of our small mixing chamber where we mix warm and cold air masses to form fog. We have a lot of measurement devices such as anemometers, temperature and relative humidity sensors. The source of the hot air comes from a heat gun, and the cold air mass is formed because we have a nitrogen heat exchanger. This is the mixing area. This is an example of one of our experiments where we created a superfog inside our chamber. There's 2 elbow ducts inlets, and we can see that the top one is almost invisible, and it's only 1 foot into the chamber. So we're definitely forming superfog. We're able to find the size distribution of the fogs that we formed here by using a PDPA, or phase Doppler particle analyzer, and we saw similar results for diameter sizes we expected. In these experiments, we created superfog, so 1.7 meters, so even thicker than superfog. We saw that it had higher liquid water content, and the particles were on the same order that we expected. In a second experiment, we had appropriate liquid water content, but the droplet size was not exactly as we had done for modeling, because this counts for a lot more larger size particles. So it had a very dense visibility, 5 meters, but not enough to be classified as superfog. So after we were comfortable with creating fog in that small chamber, we wanted to reproduce it with more controls. So this is a photo of the wind tunnel at the PSW research station, the Forest Service research station in Riverside. A major part for this project is to add climate control customization. So this is the viewing side. We usually have a camera on the left here. In the photo, there's a glycerol storage for our cooling, the copper on the side here, is our heat exchanger, and inside the heat exchanger and flow conditioner combined. On the other side of the wind tunnel, we have the water heater, and this provides relative humidity controls. So the custom cooling system, in our experiments, in the morning time we have to prep the glycerol, so we set the valve to recirculate between the cooling unit that's outside here, figure A, and then to the glycerol storage tank, figure B, and we cool down the glycerol to 20 degrees Fahrenheit. And then when it's time for the experiments in the afternoon, we change the valve direction between the copper heat exchanger, the C graph, and the glycerol storage. This is a closer look at the heat exchanger that also acts as our flow conditioner. To the right is the water heater I had mentioned before. The water heater vapor is fed through nozzles that we have here on the center of the wind tunnel, and we have temperature and relative humidity measurements just after to use as feedback for our controls monitoring temperature and relative humidity. I wanted to show a few simplified experiments. Here we're not burning any fuel, but we have a hot plate and we have a dish of water. So this serves as a water vapor source in our wind tunnel. I'll play the videos then talk over them some more. The top two videos are similar in case. The top left is at 40 degrees Fahrenheit, and there's no use of the relative humidity system, no additional water vapor compared to the right. We see there's, to the right where there's 80 relative humidity maintained, we see that there's not a major difference in the quality of fog being formed. However, in the lower left position, we have the same temperature, similar relative humidity, but this time we're burning particles upwind of the wind tunnel. We see that just before the dish we don't have any fog forming, and then suddenly we have an intense fog compared to the two events. In the last graph we just have dry fuels, pine needles burning, and we don't have any smoke forming. So from these experiments we saw that it was definitely important to have the combination of smoke and water vapor to produce very dense fogs. I wanted to mention some of the instrumentation that we have. We have many K-type thermocouples, and we have HMP45C, so these measure temperature and humidity. Here we're measuring over a basket, and in our experiments we have measurements through our fuel bed. We also had to make a custom visibility sensor in the lab to see how dense our fogs were. So these basically use the Beers-Lambert law, and it depends on the intensity that you have without fog and the intensity with fog, and depending on the geometry D, you can calculate the extinction coefficient and then calculate the visibility for the fogs we're creating. Fuel moisture content, you'll see, is very important in producing fogs. So here most of our fuels are made of, all of our fuel is pine needles, and we change the fuel moisture content by soaking them in water baths, and then we prepare them for our fuel bed, either a basket or a spread out area, and then we save a sample of our wetted fuels for later analysis on fuel moisture content using ovens and scales. So the general procedure for our experiments is we have our fuel bed, we set it on fire, we wait for it to transition into the smoldering phase, and then we can deploy our various instrumentation. So I want to talk about our controlled superfog formation experiments. this is a schematic of our wind tunnel, and we'll have a basket of pine needles and instruments and sensors downwind. The experiments, this is a summary of the experiments. The temperature range from 30 to 60 degrees Fahrenheit and relative humidities of 65 to 95. The highlighted regions, the red, orange, and yellow, correspond to reports of temperature and relative humidity conditions for each of these superfog events. The E26 or E24, these just refer to what number our experiment was. So I want to show a video about the importance of fuel moisture content when you have fires. In the top, these two experiments have very similar temperature and relative humidity conditions, both 45 degrees F and 75% humidity. The difference is the fuel moisture content. In the above graph, the fuel moisture is a little bit less than 7%, and in the lower graph, the fuel moisture content is closer to 40%. We see that there's a great difference in the quality of fog that's forming, and also great quality in the fog that's forming. Is much denser and more closer to superfog. We also did experiments with the area source. These are called our boundary layer growths. So what we did is we compared these with our SAM model. So here are the model input values for the model, and in the blue and red, these are both the model outputs, and we see in our experiment most of the smoke is encased within the model predictions. We also wanted to use our SAM model to estimate for historic superfog events like the I-4. This is just a list of parameters that we used, and we see that superfog grows very rapidly. In around 100 feet, it already travels up in height 1 yard into the driving visibility range. So that's definitely superfog forming in this case here. These are the summary of parameters that they're very important we collected that make situations very likely to form superfog. So the first is the droplet size, less than 1 micrometer. The CCN concentrations on the order of 10 to the 5th per cubic centimeter. If you have a liquid water content greater than 2 grams per kilogram, if the ambient temperature is less than 40 degrees Fahrenheit, the ambient humidity is greater than 80%. If you have fuel moisture content greater than 40%, and wind velocity is less than 1 meter per second. So this is an older version of the SAM. It's what I refer to as development, and after we've had webinars before and seminars, we've improved on it. So it won't be exactly like this, but the SAM model, I just wanted to show the things that it was capable of before. You could track the height of the superfog, and you can also get profiles of the liquid water content, profiles for temperature, and profiles for mixing ratio or the humidity. Our plan for SAM would be with prescribed burning. We'd hope that people on the ground could assist with fuel measurement characteristics, and combined with the smoke dispersion forecast that we could use as inputs for our SAM model. And the SAM model will determine whether or not we think that there's going to be superfog possible. And then we'd combine it with BP Piedmont if we thought superfog was likely to happen. And this program is very useful in tracking where the particles will be. In this example here, this is BP Piedmont tracking particles over the I-4 in 2008. So in summary, We did a lot of modeling to understand how Superfog works and did many experiments. And then we came up with a list of parameters that's very important to forming Superfog, and created a SAM model to incorporate all the things that we've been learning. So this is a photo of the Superfog, the SAM model as it is now. It's much simpler. I'm going to go switch screens to show you its use. Oops. I was using earlier, so it already has some values filled in. But the most important inputs for here are the fuel moisture. There's two options currently, wet or dry. In the future, it could be changed if necessary. The second input is fuel type. So do we have thick brush, grass and tree litters, or just grass? We have the input for temperature here in units Fahrenheit. We have the relative humidity and the wind speed in miles per hour. And we have atmospheric stability. There's options for cold and low wind speed nights, moderate and warm and cloudy. For most cases that we're interested in Superfog, we should stick to the cold and low wind speed conditions. This box here is the recommendations for if Superfog is going to happen or not. This GUI is written in MATLAB, but can be provided later for use in testing. So let's just try some cases now. So let's say we have a dry fuel bed, and I will use a thick brush conditions. I'll leave the surface temperature at 40 degrees Fahrenheit and humidity at 80%. 2 mile per hour wind speeds. And then all you have to do is after you fill in the areas, press start. And it may take anywhere from 10 to 30 seconds to calculate. Oh, it changed. So for these kind of conditions, we think Superfog is possible. So it should. So possible is the outcome of this case. If we changed it to now wet, so that's increased fuel moisture, and run the code again. It produces one of the other outcomes we have. The Superfog is very likely. Under this recommendation, it's strongly recommended to move to using the BP Piedmont and seeing if the smoke will travel again along roadways, interrupting visibility. Other conditions, if we had less of a fuel source like grass or tree litter, let's say, for same temperature and humidity conditions. We have this is another possible outcome. Superfog is not likely. So these conditions we don't think need to be worried about. And just for example of the last recommendation that the model can live, we're going to use fuel type grass. This has lower heat and lower vapor production. So yeah, the recommendation here is Superfog 0 threat, so there's absolutely no reason to worry about it in this case. That's all I have for my demo of Superfog.
Okay, well, thank you, Christian. So this was a brief run through experiments and how everything resulted in a formulation of our SAM models. I guess now we are open for questions.
Okay. Well, thank you guys. That was it's very interesting, and that the science behind a model that is very user friendly was really interesting. That was very interesting to see how that all came together. There's a couple questions have already come in, and I'll read those out. But if you have some questions, go ahead and send them in, and we'll work our way down the list. Sorry for my voice is a little gone here. I've been battling some flu, but I think I can get through it here. The first question comes from Gary Curcio, and he says, FMC is only for dead fuels, or does this include live fuels that are being consumed or damaged by fire?
I consider this as a dry fuel moisture like content in our so this would be like a wet ground, damp areas, additional fuel moisture content. In our laboratory experiments, fuel moisture content is kind of added to dead fuels. We have kind of dead pine needles, and we were soaking them in vats. So I think it was, yeah, so it would be much related to like dead fuels.
Okay.
Or maybe in the future we can talk more about changes if it's necessary for live fuel moisture content.
Okay.
Well, maybe follow up. Why would be it? I mean, it should be the same, right? Either is live or live or dead. I mean, we are just considering additional water input into the atmosphere from fuel. So as long as you can evaporate it from fuel, it should be the same.
Okay. Gary also asks, can superfog occur with temperatures up to 70 degrees?
No, I don't think it's likely. No.
Okay. What's the maximum you think?
Maximum? Maybe we had experiments where we had 60 in the environment, and we had those very wet fuels, and those could produce the superfog. The experiments were also done in Riverside, so it's very hot out here. So our our climate control, can only fight it so much. So we were doing experiments of 70 degrees Fahrenheit and 80, and we were having trouble forming any that much smoke in our experiments at 70 and 80.
Okay. Philip Manuel asks, is it possible to have the SAM model added as an app within Behave Plus?
I'm sorry, I don't know what Behave Plus is. Do you know, Josh?
I mean, I'm not super familiar with it, but it's it's a sort of one of the models that's used to predict fire behavior.
We are distributing this SAM model as executable, so I mean it can be connected with most of other models. So I presume the answer should be yes, because it's independent model and it's its own executable module.
Okay.
So I mean, the point is, Christian is showing here this simple interface. But these numbers, we can make it in such a way that these inputs are coming from any other model, and also then this output, which is in this case only zero superfog thread or superfog is very likely or unlikely. That basically comes based on our estimates of visibility and thickness of that impaired visibility layer. So we can directly feed that impaired visibility layer, its thickness, its depth into other models. So here we just made it as simple as possible. So manual input with several easy to understand outputs. But actually output can be really complex. I mean, it's It's particle number, it's concentration, it's particle size, it's liquid water content, its boundary layer depth. So all this is hidden under this zero superfog threat.
Okay. Kent Prochaska asks, what height is the wind measurement using? Eye level, 20 feet or 20 feet?
This is like eye level, maybe 2 meter tall.
Okay.
Yeah.
Alan Long asks, is PB Piedmont linked within SAM, or does a user have to go to PB Piedmont separately?
Currently, you'd have to go separately.
Okay. Alan also asks, is SAM accessible now for fire manager use? Is this something that somebody could link into?
Sure. Let me.
Yeah, I mean, so it is available, right? So whoever wants can have it. Maybe it's even on, I believe some old version is posted maybe on Joint Fire Science Program website. Yeah, we will give a new version, but I'm not sure. It's basically still not approved for any kind of decision making. But so it's kind of, we call it beta version. So it's I'm not sure. Yeah, so we believe it works and so on, and we would like more and more fire managers to use it, but as beta version, and then eventually we can declare it, yes, that's reliable, field tested. I mean, so far this model will reproduce all Superfog events in the past. Now it's we would like to kind of use it for forecast.
Right.
I mean, a new thing. So your answer is yes, it is available.
Okay. Richard Watling asks, where does SAM get droplet diameter and CCN number, fuel type, and also fuel type?
Oh, so let me see. So SAM isn't exactly fed with the CCN number and diameter, but we use our calculations using we know liquid water content and what's likely to form superfog. There's been a paper before from biomass burning that concentrations are 5 orders higher, so 10 to the 10 per cubic centimeter. So there's definitely enough condensation sources for our water vapor. The SAM tracks liquid water content through its calculations, and when you have 2 grams per kilogram, that's a superfog position. Yeah.
Okay. Andrew Rondazzo asks, do you suggest avoiding prescribed burn when superfog is possible?
I
think it might be avoided if you get the message for superfog is very likely. When superfog is possible, there's a slight chance that it might not happen, and I think we still need further testing in the future that people could use and report back, because we don't have many field tests for the SAM.
If superfog is possible, and then you have a wind speed that will likely direct it away from major roadways and so on, then I guess you would go for it. But if you are likely to impact some close major roadway, then probably don't do it. So
okay.
There are other factors.
Yeah.
Okay. Did you look at the effects of suppression action? This is from Ralph Gonzalez. Did you look at the effects of suppression action using water in the creation of superfog? So could the water that's used to suppress the fire, could that actually stimulate superfog development?
We haven't looked into that, but it's possible. I remember going to a prescribed burn, and they had a helicopter extinguishing the fire from a nearby water source, and that was creating extremely dense fogs. But superfog is more of a nighttime phenomena, so you know, the extinguishing part is usually during the day or just before nighttime. So I haven't looked into suppression causing superfog.
And my guess is, I mean, it won't be long-lasting suppression because, right? So it's just my guess. And here, during nighttime, it can be slow smoldering. You keep on adding moisture gradually. It's cold. Keep on condensing immediately. So somehow I get the impression that suppression of a fire may not lead for a sustainable superfog. You may have something that will last order of minutes, I guess. Mm-hmm. That's my guess. I'm asking also for any input.
Okay. Scott Kennedy says that he was on the Dismal Swamp fire, and the low temperatures when superfog occurred were above 60 degrees. Just sort of a comment there. Everyone to respond.
Yeah, here in Rivers, as Christian said, in the lab, we were forming it with 60 degrees. But you know, yeah, I mean, all other parameters then also have to be extreme. So very moist fuel, humidity in the air, and yeah, enough smoke. So yeah, we did in the lab. But those are, I presume, rare cases. And with some yeah,
okay.
so
Okay, Joe Royce has a question I was thinking of myself, and it was, is superfog a continuum of smoke-fog combinations, or are there conditions sort of a trigger for the condition?
I would say it's continuation. I mean, it's when visibility of a fog goes under 10 feet, then that is when we start calling it superfog. So
okay.
That's how I guess Gary Ackmeyer formulated it, and we keep that definition. So there is no step function that will take you from regular fog to superfog. It's just visibility drops gradually.
Okay. Kent Prochaska asks, using the graphs in the earlier slides, is it possible to estimate the distance from source that the superfog will extend?
The graphs that I had here, in this case, there's it was a continuous fuel source. So we would have to make a little bit of a modification for like in the model for no source, and then see how far it'll travel. BP I think will show the direction they will head, but I don't know for sustainable. Yeah.
Okay. Benzo, hopefully I got your name right there. All of these data were obtained from fog chamber, correct? Was there a test with NWP, with the NWP model done?
I mean, so we had two chambers, yeah, that big wind tunnel and that small chamber. And then we were using field data for whatever these cases we had available. And NWP is...
I'm not familiar with NWP.
I'm not sure either. Maybe, Ben, if you can write in and explain what NWP is, maybe we can get back to that one.
Whatever field data we had available, that is inside the SEM model. And, of course, our laboratory wind tunnel data. All the Gary Ackmeyer's data, some NWP and
okay. Gary Curcio writes again, you mentioned linking it to PB Piedmont. Has this been done? If not, why not link it to WRCC's effort to make PB Piedmont available on the internet? Just
there is no good excuse why it's not done yet. So we just need to sit down and do it. And it's, you see, we are still testing how much interest is there for this to be done.
okay.
So I guess if there is big interest, we will proceed in that direction. We have that idea as Christian presented. Yeah, it was not done.
Somebody for the question above, Sean Lukes wrote in and said NWP stands for numerical weather prediction.
Oh, so it's not model. Yeah, so you are saying like war for MM5 and so on. Yeah, you know, that would be the easiest way to do it. The only problem is then, yeah, I mean that definitely can be done, but you know, running model like war for MM5, which now nobody runs anymore MM5, it's not anymore user friendly.
Mm-hmm.
So it's kind of different dimension there. That's my opinion. Yeah.
Okay.
Definitely, I mean, any numerical weather prediction will give you exact inputs that you need for SAM. Yeah.
Right. Okay.
So if you have available output, so I mean, then just use it and put it in. Okay.
Okay. Richard Watling asks, how do you derive microphysical variables from macrophysical observations?
So what you are putting here, macro is kind of, you can see it as boundary conditions, right? So you kind of put soil moisture, you put ground temperature, you put the fuel type, right? And that kind of drives our governing equation, which is for energy, momentum, and concentration. And we couple those equations. Basically, you input boundary conditions and initial conditions for our advection diffusion model that then later basically changes the phase of velocity of water, grows boundary layer over the fuel bed. There is Christian didn't show actual model formulation, but those are just primitive equations for momentum, energy, and phase change. Yeah.
Yeah, phase change and concentration of water vapor.
So it's kind of two-dimensional Navier-Stokes equation coupled with the energy and thermodynamics. What was that the question?
Okay. Michael Dewitt asks, has this been compared to the National Weather Service's LVORI, Low Visibility Occurrence Risk Index? We have many events of fog when the nighttime temperatures are above 70 degrees.
No, I haven't compared it with the Labori. I'm familiar with what that is, but I haven't used it. Labori, from my understanding, uses a lot of time, but there's no input from what kind of fuel there is. So, you know, there's going to be more water vapor production or less water production. So those are going to be some two differences when we would compare SAM versus Labori.
Okay. Gary Curcio has a comment. He says, in one of the slides you mentioned visibility was 5 meters or 16 feet, therefore not a superfog event. However, to stop a vehicle going 55 miles per hour, the recommended stopping distance is 230 feet. So even a 16-foot visibility is unsafe, and the only speed is 10 miles per hour, where the distance is 17 feet. Just a comment. Okay. Mindy Wright asks, did you say that SAM is or isn't available on JFSP? Do you guys know if it is?
I remember it was submitted together with the, old version, right? was submitted together with report, and I know report is available, so I honestly never tried to download the SAM. So, but just Christian is giving you our email, so just send us email and we will send you SAM.
Okay. All right, so the last questions come from Kent Hanby, and he asks, the moisture of extinction for fuel model 2 is 15%. How does that relate to a fuel moisture of 40%? And where does the dew point factor in?
I'm sorry, can you say that one more time?
It says the moisture of extinction for fuel model 2 is 15%. How does that relate to a fuel moisture of 40%? And where does the dew point factor in?
Fuel model 2. I'm not familiar with the model they're referring to. Fuel model 2. Extinctions.
Yeah, this one's out of my
Yeah.
level expert. I'm not sure either. So Ken, if you can maybe explain that. Or the fact that we don't know what fuel model 2 is might answer the question.
Please keep in mind that even when the webinar is over, we are looking for your questions or comments through email. It's easy to find us online. So yeah, I'm sorry, I also don't know how to answer this question.
Okay. Well, if there are other questions out there, that's the last ones that we have in the list here. So if you would like to contact Dr. Princevac or Christian, the email is up there. You can contact them and continue the discussion further. But other than that, I'd like to thank both of you for an interesting presentation. There's some stuff I think that's going to be really important, especially in parts of the country where this is a common occurrence. And we look forward to hearing more about it. Thanks, guys.
Thank you.
Thank you.
And thanks everyone for coming to the webinar, and check on Advances in Fire Practice for upcoming webinars. There's if you're interested in smoke, there's quite a few smoke research webinars coming up in the next few months. Thanks everybody.
Thank you, Josh.